Aluminium is a chemical element with the symbol Al and atomic number 13. It is a lightweight, silvery white metal that is highly reactive. When exposed to air, it forms a protective layer of oxide on its surface, which is why aluminium does not occur in metallic form in nature but rather in compound form. Aluminium is the third most abundant element in the Earth's crust, following oxygen and silicon. It is the most widely used non-ferrous metal and the second most used metal overall, after steel. The metal has a relatively low density, high electrical and thermal conductivity, excellent corrosion resistance, and can be alloyed to achieve a high strength-to-weight ratio. Additionally, aluminium can be recycled indefinitely without losing its quality, making it a sustainable material. Aluminium is also ductile and malleable, meaning it can be easily drawn into wire or hammered into thin sheets, which allows for versatility in various manufacturing processes. This wide range of applications cuts across several industries including transportation, used in aircraft, automobiles, trains, and ships. Construction, for buildings, bridges, and roofing. Packaging, for cans, foils, and containers. Electrical, in wiring, cables, and electronics. Consumer goods, such as appliances, cookware, and furniture. So, how is this valuable metallic element extracted from its ores? This is what we will look at in this video. Welcome to the channel. There are several minerals in the world from which aluminium can be extracted, but the most common raw material is bauxite. Aluminium is typically extracted from bauxite ore using the bioprocess, and then refined through the Hall-Héroult process. Bauxite is a weathered rock that contains two forms of hydrated aluminium oxide, predominantly monohydrate in caustic bauxite, and primary trihydrate in lateritic bauxite. In addition to these compounds, bauxite also contains iron oxide, which often gives it a reddish-brown color, as well as silicates, such as clay and quartz, and titanium oxide. The bioprocess. The bioprocess consists basically of four stages: digestion, filtration and settlings, precipitation, and calcination. 1. Digestion. After the bauxites from the mine are crushed and ground, it is then mixed with a solution of caustic soda and pumped into large autoclaves. The bauxites, caustic soda, and hot water are digested at temperatures ranging from 110 degrees Celsius to 270 degrees Celsius. During this stage, alumina dissolves, while silica, iron oxide, and other impurities remain insoluble. It is important to note that bauxite primarily consists of two oxides, alumina and iron 3 oxide. Alumina, also known as aluminium oxide, is an amphoteric oxide, meaning it can react with both acids and bases, while iron 3 oxide is a basic oxide. The alumina in the bauxites dissolves to form sodium aluminate, while the silica reacts and precipitates from the solution as sodium aluminium silicates. Iron oxide, titanium, and other impurities remain chemically unaffected. The chemical reaction responsible for the digestion of alumina is as follows. Alumina or aluminium oxide is digested in sodium hydroxide, also known as caustic soda, which is an alkaline solution to give sodium aluminate and water. The use of an alkaline solution for digesting bauxite is crucial because iron 3 oxide, being a basic oxide, does not react with the alkali. In contrast, the amphoteric alumina dissolves in the alkaline forming sodium aluminate 3. 2. Filtration and settling. Once the digestion process is complete, the resulting solution is cooled to atmospheric boiling temperature. The red mud, which consists of insoluble iron 3 oxide and other impurities, is partially separated by decantation in settling tanks before being disposed of in designated ponds. 3. Precipitation. The liquid sodium aluminate is cooled until it becomes supersaturated and then seeded with aluminium hydroxide crystals which gradually settle out of the solution. The chemical reaction is as follows. Sodium aluminate, seeded with aluminium hydroxide crystals, gives an alkaline and aluminium hydroxide. The underlying principle here is to use a common ion in the solution to reduce the solubility of specific ions. In this case, aluminium ions are present in the solution, so pure crystals of aluminium hydroxide are introduced to distort the equilibrium position. This increases the concentration of aluminium ions in the solution, shifting the equilibrium to the right and thereby precipitating aluminium hydroxide. The resulting hydroxide precipitate is separated using vacuum filters and washed with clean water. 4. Calcination. Finally, the aluminium hydroxide crystals are heated at a temperature exceeding 1000 degrees Celsius in a rotating kiln or fluidized bed. This calcination process removes water and converts the hydroxide into a dry white powder. The final product is technically pure alumina. The next step in the extraction of aluminium is the electrolysis of alumina. The method for obtaining aluminium from alumina through electrolysis was invented by Charles Hall and Paul Héroult in 1886. This process is known as the Hall-Héroult process. The Hall-Héroult process involves dissolving aluminium oxide, alumina, in molten cryolite and using electrolysis to separate aluminium from oxygen. An aluminium smelter typically comprises one or more pot lines, each containing about 125 to 150 electrolytic cells. Each cells consist of a carbon-lined steel shell, which serves as the cathode, a carbon block acting as the anode, and a molten bath of natural or synthetic cryolite. The electrolysis of alumina occurs within this cryolite bath. Cryolite helps lower the melting point of alumina from 2000 degrees Celsius to about 900 degrees Celsius, thereby reducing production costs. Electric current enters the cell through the anode blocks, which are suspended in the molten electrolyte bath of cryolite and alumina. In this molten salt bath, aluminium oxide, alumina, is electrolyzed into aluminium and oxygen gas. At the cathode, aluminium is produced through a reduction reaction process, while oxygen gas is generated at the anode via an oxidation reaction process. The oxygen reacts with the carbon anode, producing bubbles of carbon monoxide and carbon dioxide gas. The liquid aluminium, being denser than the electrolyte, settles at the bottom of the cell. Periodically, this aluminium is siphoned off using a vacuum and transferred into crucibles. The overall reaction for the Hall-Héroult process is given as follows. In conclusion, aluminium smelting is a vital process that produces a material essential to modern society. Aluminium plays a significant role due to its unique properties, availability, and recyclability, ensuring its continued importance in the years to come. If you found this video helpful, please remember to like and share it. Don't forget to subscribe to the channel, and turn on the notification bell for more content. Thank you for watching, and I'll see you in the next video. Goodbye.